Okay, and hopefully this works. So if those of you that are gone today, this is the recording for the beginning portion of Unit 3 for Systems and Conservation Laws. So students in here today that are present are sharing the answers to the pie chart here. Anyone taking a guess for me? Which one is the highest percentage? 35.7. Which one goes there? Thanks, Cole. Coal, thank you. It is not coal. It's petroleum. That's okay. How about 33.3%? Next one. You're going to get it right once.
Is it coal?
Natural gas. We should do like a game show, right? Natural gas. Now, I don't know how accurate this thing is. It might not be accurate. I got this from the internet. I don't know if you guys have heard of that before. 13.1%. What's next?
Coal.
Coal. What the heck?
Is coal like non-existent or something?
Apparently.
That's all they use.
I can't tell you if this is accurate or not. I did not cite the source.
I think they're lying to you.
What's 9.8%?
Nuclear. Coal.
It's coal. All right, and then finally, the last one is the nuclear. Now, whether or not this is accurate, I don't quite know. It's always changing. But would you guys agree that energy is something that's always talked about in the news? I mean, would you guys agree? Pretty important to the way the world works is this energy concept. Now, we're not going to do a lot with fossil fuels and coal and all that kind of stuff. We're looking at this from a standpoint of what energy actually is. And so as we move into this unit, before we start, I got to talk about a review of 4 key things that you should have heard before, but you might not have fully understood. So energy is just the ability to get things done. Now, when I put things in there, things is in quotation marks, if you will. What do we mean by things? It's getting stuff done. The ability it's hard to define what energy is. If you were to Google what is energy, it's a very difficult thing to define. It is strongly related to what you guys read about. And that quantity you guys read about is something called work. But energy is really hard to define. It has huge global implications. Would you guys agree that sometimes wars are fought over energy? Right? So energy itself is something that's foundational and fundamental to the way the world gets things done. So it has huge implications. You guys have certainly heard of the law of conservation of energy, correct? You've heard of it? Raise your hand. Students are raising their hand. You can't see them right now, but raise your hand if you've ever used the law of conservation of energy in a science class to actually solve problems, to actually quantify things. Most people have not. You've heard of this quantity, this thing called energy is conserved, but most people don't quantify this until you get into a physics class. Now, for those of you that maybe have been in a chemistry class and you've balanced equations, have you guys done any balancing equations? You might say that that's applying a conservation of mass idea, but in reality, mass and energy are very related to this Einstein-Stangers equation. So I want to take a moment and see that you've heard of this before. E equals mc squared. You've heard of it? Okay. Yeah. So you had to have, because this is what made Einstein famous. This is not why Einstein won his Nobel Peace Prize in physics. It was not for this equation. Energy, E stands for energy, M stands for mass. What's C stand for? The speed of light squared. Now the idea behind this is that what Einstein gave us was he showed us how to determine the energy contained in matter. Now I want to take a moment and just talk about something called fusion. Because you notice that nuclear reaction was a part of our pi structure. All of our reactors are fission reactors. This is showing you a fusion process. And so the energy is equal to mc squared has to do with something called mass defect. And I don't know if you've heard of this thing before. Mass defect has to do with how the masses change as we start putting these things together. If I take this thing here, it looks like it's got a single proton and a single neutron. And then I take it and I fuse it with this thing. It looks like it's got 2 protons and 1 neutron. If I were to put these things onto a scale and read it, it's going to have a certain amount of mass. If it was in a chemistry class, it would read AMU, so many atomic mass units. Put that on a scale, it weighs a certain amount. Then I go through and I fuse them together, and you notice I have the same amount of parts over here. Do you guys notice I have like 3 of these bluish and 2 of these? See, I still have the same law? I put these on a scale, and what we find is that when we put them together into a fused element, they weigh differently. And you might say, well, that's weird. You take these pieces, you put them together, and you say, well, when I put them together on a scale, they actually weigh a different amount than when they're separate. What the difference is here, this over here is bigger than that. They would weigh more separate than when they're connected together. The difference there is what's called mass defect. That mass defect is what goes into that E equals mc squared equation. So when I go through a fusion reaction and the sun is fusing hydrogen into helium, the mass is becoming smaller. And where's that mass going? It's getting converted into energy. So there's a difference in masses there between those. Are you taught that in chemistry when you get into nuclear stuff? Do you guys do anything with that? Okay. Anyway, that's Einstein's famous equation. So technically, it's really not the law of conservation of energy. It's not the law of conservation of mass. It really should be stated as the law of conservation of mass and energy because they're equivalent kinds of things. So again, you've probably heard of that before. We're going to quantify the conservation law. Many forms of energy, but in general, there's two types. There's potential and kinetic, and I'm certain that you've heard of these before. You guys know that kinetic is energy of motion, and potential energy is energy of position. So we're going to quantify those, put some numbers to it. And then finally, last one is that potential energy is force specific. So there are potential energies associated with the four fundamental forces of nature. There's gravitational potential energy, there's elastic potential energy, there's electric potential energy, there's strong and weak nuclear potential energy. So potential energy is force specific, it is recoverable. So what that means is we can get that energy back. When we store energy as potential energy, we can get it back. Okay, so we're gonna those four things as far as energy review are things that you should have heard of before, but it sort of serves as a foundation for us starting this unit. Let's talk about the unit of energy. The unit of energy that we're going to look at, none of this was probably in your reading. I think it just assumed that you understood some things about this. The SI unit that we use is the joule. It's the one that we'll use most often. It is equivalent to the amount of energy expended or transferred when a 1 Newton force moves an object a distance of 1 meter. So when we talk about energy and we talk about the units for it, it's about force acting through a displacement. The force measured in newtons, the displacement measured in meters. We can say that 1 joule is 1 Newton meter. Notice I did not say per. I did not say Newton per meter. A joule is a Newton meter. It's equivalent to 1 Newton of force acting through a distance of 1 meter. Are you guys force calibrated yet? Okay. I want you to do a little motion with that person you're seated next to. Okay, so I want you to push on that hand. Push on that hand. Push on the hand up. Okay, push with 1 Newton of force. Push with 1 Newton of force, and then move that hand 1 meter. You ready? Go. Move it 1 meter. Now you're gonna have to stand up. Go. Push it 1 meter. 1 Newton of force. 1 meter. Go. 1 Newton of force. Keep going. Keep going. 1 meter. Go. Go. You gotta push. 1 meter. You gotta go. Push. This way. Push. 1 meter. Logan just transferred 1 joule of energy to me, and you did that by exerting a force of 1 Newton through 1 meter. Now, that's the idea of energy. Other familiar units. If you eat a Snickers bar, you don't measure the energy content in joules. What do you measure then? The calorie. It's technically a kilocalorie, but 1 calorie by definition would take 1 gram of water and raise it 1 degree Celsius. So this is defining a unit of energy called the calorie. Technically, 1 food calorie is 1,000 of those calories. Anyone know what the? Can I share a story with you? Last night I'm sitting there grading your quizzes, sitting on my couch grading these quizzes. My wife comes home. She had to work late last night, so she comes home. She's like, "Mr. Isaac, I don't know why she's going to Mr. Isaac. Is it cold in here?" I said, "It doesn't feel cold." And she looks at the thermometer, the thermostat, and it says it's 65 in the house, where the thermometer is set for 68. She goes, "Something's wrong with the furnace." So I'm sitting there going, "Oh my gosh, I better go check." So I go down, check the furnace. Raise your hand if you've ever looked at the furnace. Yeah, so I open it up, I look at it, I see there's no pilot light on it, but that's okay because the pilot light is, this is one of those things that doesn't have a pilot light. It uses like a little burner thing, it ignites it, just using electrical heat. Nothing up, I smell a little bit of gas, I'm like, ooh, something's coming. I tried troubleshooting, tried fixing it, nothing. So I ended up having to call last night to get a furnace repair person out. You know how much they charge just to come out? About $100 just to show up. Okay, yep, I'll come take a look at it. $100 just to show up. You know how much they charge for the actual service call? Like another $150 or something like that, just to go through and fix it. It was a very simple fix, but I couldn't figure it out. Anyway, we now have heat, so I'm happy for that. If I were to look at the rating on the furnace, how would it measure the amount of energy it can deliver? What would be the unit for it? It's very common for burning kinds of things. Thank you. The BTU. The BTU stands for British Thermal Unit. So often we'll measure energy content for heating systems using the BTU. What it does is it takes 1 pound of water and raise it 1 degree Fahrenheit. Again, you notice what I'm doing here is I'm changing something. In this case, I'm changing water by a certain amount of temperature. And so the BTU is defined based on water. Now, how about for electrical energy? If I lose power, anyone lose power the last time we had like a winter storm coming through? Did you guys lose power?
Yeah,
Like how long were you without power?
30, 45 minutes.
Oh, that's not 30, 45 minutes, not a big deal. Your fridge is fine. It'll maintain temperature for a little bit. If you start losing power for a day or something like that, now you got to start worrying about food spoiling and stuff like that. So you might use a generator to go through and power the house with a generator. How would you measure electrical energy? What unit would you use? Thank you. The kilowatt is actually a unit of power. It's not the kilowatt. Kilowatt is a unit of power.
Amperium?
Say it one more time.
Amperium?
Barium?
No, amperium.
Ampere?
I don't think so.
Is that Spanish?
Yeah.
Thank you. It's a kilowatt hour. The kilowatt hour. Now, the electrical energy unit that we use is something called the kilowatt hour. Now, I'm not going to be able to get into electricity stuff until we get into chapter unit or semester 2, but I'm going to show you a kilowatt hour energy meter. I took it from my neighbor's house. I didn't realize it. Yeah, but I took it off where the electrical power comes in. I took this thing off. And so this is a kilowatt. That'd be like a federal offense, right? So, oh my gosh, I'm recording that. So, no, I'm just kidding. I did not actually do that. Anyway, this is a kilowatt hour meter upside down. So kilowatt hour is a unit of energy. The idea behind this is when you have your toaster plugged in, you have your hair dryer turned on. The more stuff you're using electrically wise, the faster this little dial will turn. And then inside of this, there's a whole bunch of gears here that will turn. Will just basically move the meter ahead. So the more things you have on, the faster this little dial will turn. Now, most of these things have been replaced with electronic versions, so this is a mechanical unit. Most of them today are tied into. Have you guys heard of the internet? Yeah, so they're tied into the actual internet. So if you lose power, you probably did not have to call consumers that you lost power. They already knew because most of the energy meters that are outside the house are now online. So anyway, that's by the way, a kilowatt hour will run a toaster for about an hour. A toaster is about a 1 kilowatt device. To run that thing for an hour, it takes 1 kilowatt hour of energy. Now, raise your hand. You've gotten your gas tank filled recently. What's gas cost right now?
Yesterday when I got it, or maybe 2 days ago, it was like $2.60.
It's below $3 now? Nice. A lot of people say gas is super expensive. What I'd like to do is I'd like to put gasoline energy into other forms. So a gallon of gas contains a tremendous amount of energy. What I want to do is it's equivalent to 120 million joules of energy. Now to put that in perspective, you push my hand 1 meter. If you exert 1 unit of force through 1 meter, you do 1 joule of work. A gallon of gas, if I had a gallon of gas push on something, convert it so they can actually convert that energy into something useful, I could push 1 Newton for 120 million meters. Right, and that's to put that in perspective. So you can move something a really long distance. Let's put it in BTUs. It is equivalent to 114,000 BTUs. Now, a standard pool in your backyard has about 114,000 pounds of water. About. A standard up above ground pool, 10,000 gallons, whatever it is, about 114,000 pounds. If I were to burn that gas and put the energy from that combustion into the water, it'd take that water and raise it by about 1 degree Fahrenheit, which doesn't seem like much, but it's really hard to change water's temperature. So that's a tremendous amount of energy. How many kilowatt hours? Well, that is equivalent to about 33.41 kilowatt hours of energy. Meaning, if I were to run a generator with that gallon of gas, pour that into my generator, and I run my toaster, I could run my toaster for 33.4 hours with that gallon of gas. Now, usually, if I lose power, I don't run my toaster. I run my fridge. I run my furnace, which is not working. But that's how much energy it contains. Let's talk about food. What's the standard diet for someone your age? What do you typically consume a day for food? 2,500 calories? 2,000 to 2,500 calories? If you're an athlete, like, I know, if you're an athlete, you're probably eating a lot more than that with hockey. How many? About 4,000? Okay. 6,000? I got you. But let's just do a standard. Food FDA says 2,000 calories per day. How many food calories is a gallon of gas equivalent to? It's about 30. Hello. It's about 31,500 food calories. Now, I want to stop and put this in perspective for a second. 31,500 food calories. About how many days worth of food would that be? 31,500, divide that by 2,000 calories. That would be about 15, 16 days worth of 3 meals a day food. Now, when people say gasoline is expensive, that would be equivalent to about 45 meals. What would 45? No, don't drink gasoline. Is that what you're saying? You cannot drink gasoline. That's not the right kind of fuel for your body. It works fine for your car, but not for your body. This is a huge amount of what's called energy density. So, when I use the term energy density, do you guys know what that means when I say it's energy dense? In a very small amount of volume, I have a tremendous amount of energy that I can do stuff with. One of the challenges between internal combustion cars versus battery-operated cars. Anyone hear the debates about should we go with electric cars versus internal combustion? It's a debate. It's been going on for quite some time. One of the challenges is gasoline in a 20-gallon tank of gas. You have a tremendous amount of energy. I mean, a tremendous amount. In order for us to replace that chemical potential energy, which is what that is, with electric potential energy from a battery, it's really difficult to do that. That's because of the density of that fuel. There's a reason that we're so addicted to gasoline. It's because it's got so much energy in a small amount of space. Go ahead, say it again.
No.
Good? All right. Let's move on. Now, folks, we're going to start moving into actually this quantity called work now. So your reading really started here. Conceptually, work is the means by which we transfer energy. So work is a verb. It's a means by we transfer energy between objects. Positive work increases energy. Negative work decreases it. If force is constant and it acts in the direction of motion, and sometimes it is, oftentimes it's not. If force is constant, acts in the direction of motion, then it's simply a product of force and distance. This is all I can do in my one semester class. One semester class does not deal with forces being a vector, displacements being a vector. These things are not always aligned. So even though we can say work is simply a product of force and distance, we have to be a little bit more careful with that because force is a vector. First, I want to show you what we mean by positive work. So positive work is when the force and the displacement are in the same direction. So I do a lot with throwing objects around, and so here we have a baseball player throwing a ball, and I'd like to do this with Mike. You okay with that?
Yeah.
Actually, I'm not gonna do the baseball. I'm gonna do the,
You don't trust me?
no, it's not that I don't trust you. I don't trust my ability to throw that accurately. So when I throw this ball toward you, I'm doing positive work on that ball. You notice what I'm doing is I'm exerting a force in the direction I'm moving it. So what I'm doing is, can you guys see that I'm adding energy to this thing? It's not your first day as a human, so you've heard of different forms of energy. When I throw it, what kind of energy am I actually giving it? What would be the energy of its motion? I'm putting some work into changing its kinetic energy. I'm doing positive work when I throw it. You notice I'm exerting a force in the direction that it's moving. Now, when I catch it, which way am I exerting force? When I catch it, which way am I exerting force on its motion? That way. Which way is the ball moving? This way. So when I throw it, I'm doing positive work. When you catch it, you're doing negative work. Throw it, you do positive. I catch it, I do negative. I'm increasing the energy, you're decreasing the energy. You're increasing, I decrease it. So you can think of work as a means by which we transfer energy between objects. For lunch, I had just a, what did I have? A little BLT, bacon, lettuce, tomato sandwich, right? So that energy that I consumed in that food, I'm using some of that energy to throw that ball. Of course, what do you have for lunch?
Pizza.
Pizza, all right. Yours is probably more energy dense than mine, right? But you use some of that energy from that pizza to do some work on that ball.
Yeah.
So there you go. Work is a transfer of energy. All right. Now, what about if force is not aligned? Oh, by the way, let's update that for people watching the video at home. Let's draw some things on here. Force is a vector. Displacement is a vector. So I'm going to say that that force and that displacement act together to do some work. Because they are aligned, that's positive work. Now, when this guy catches it, the direction of force that he exerts is towards the right, whereas the direction of motion is towards the left. So I forgot what colors I'm using here. But the direction of force that he's exerting is this way, whereas the direction of the displacement is this way. So in one case, you're doing positive work, in the other case, you're doing negative work. Now, what about when the force and the displacement are not along the same line? You guys read an equation, right? You guys could tell me what the equation is. That's a modifier to work is equal to F times D. You guys did some reading. How would I determine the amount of work done by that tension force, which is not completely aligned with that motion? Thank you, Julian. Okay, so let's go ahead and write that down. This is the formal equation for us. F times D times the cosine of theta, where theta is the angle between these two vectors. So theta, when I take the cosine, when I take F times cosine of theta, what I'm doing is I'm getting how much of that force is in the direction of D. And so I have to be careful with that. Sometimes I'm given theta to be the angle between the two things, and sometimes I'm given a different angle. So I have to know why that cosine of theta is in there. It's to get me the component of force that's in the direction of the displacement. I'm going to do a few problems with you. So just three of them here, and again, these are fairly straightforward to do. Pay attention to your signs, and whether or not you're doing positive or negative work there. All right, let's try this. Bob and Tom, do you know why they call that a bobsled? Because one of the two athletes are usually named Bob. I don't know if you knew that or not, so they call it a bobsled. So Bob and Tom are pushing on this. It's not true. I made it. All right, two athletes push on a 250-kilogram sled. Both push for 12 meters, but Tom pushes with a force of 150 newtons. Bob pushes 180 newtons at an angle of 15 degrees below the horizontal. Friction between the sled and the ice, 25 newtons. How much work was done by each object? There's really three objects doing work. One is Bob, one is Tom, the other is the ice. And so what was the total amount of energy transferred to the sled? So let's go ahead and try this. So the work done by Tom, let's do that first. The force that Tom exerts, multiplied by the distance that Tom exerts that force, multiplied by the cosine of the angle between that force and that displacement. let's see. Tom pushes 150 for 12 meters. What is theta for Tom? The cosine of 0 is 1. So when I'm going to use this equation, the angle between the force that Tom exerts and the displacement of the bobsled is 0 degrees. He's pushing it horizontally. So all of the force he exerts does work. I think that's 1,800 joules. I think. Yeah. Sounds right. All right. So Tom does 1,800 joules of work. Now let's do what Bob does. So the work done by Bob is the force that Bob exerts, multiplied by the distance that Bob exerts that force, multiplied by the cosine of the angle between them. Now, I know the numbers there. What I want to do is I want to put down that 15 degrees. First, should I put it in as a positive or a negative? It's below the horizontal. So if I were to draw an FBD, you guys are tired of drawing FBDs, right? But if I were to draw an FBD, the force that Bob is exerting is downward at an angle. Should I put in a cosine of 15 or negative 15? It is, and that's my point that I want you guys to realize. I don't care if it's above or below the horizontal. The cosine of negative 15 is the same as the cosine of 15 degrees. They both are projected somewhat in the direction of that motion. So in one case it might be below the horizontal, in the other case above, but the component that's pointed that way is the same. So I don't care whether or not it's cosine of negative 15 or 15. All right, what is the amount of work that Bob does? And again, just help me out if you can do that for me. It's 150 times 12, but it's got that cosine. Or I'm sorry, it's 180 times 12.
That's like 2,086.
Thank you, 2,086. Still positive. Finally, the work done by the ice. Now, the ice is able to do work through friction. And so let's go ahead and do that one. So let's see. Let's use brown for that one. So the work done by the ice is the force the ice exerts, multiplied by the distance through which that ice exerts that force, multiplied by the cosine of the angle between the force of friction and the displacement. Turn and tell that person that you're sitting next to what theta is for the ice and the bobsled. Take a moment. Talk that over. They're spinning their wheels. They're not able to, if you're watching this at home, they're all like, they're spinning. I haven't heard the correct answer yet. Someone please raise a hand. Thank you, Colton. You're the only one that's actually participated today. So thank you. Everyone else they're lost in their own never know. All right, 180 degrees, and that will give me a -1 for that. So anytime I'm using the work is equal to FD cosine theta, just think about which way that force and the displacement are aligned. I don't see 180 anywhere in that problem, but I do know that friction opposes motion. So I can now just go ahead and do 25 times 12. What is that? 300? How much? 300. 300? What's different about this is that it's negative work. And that's because that force of friction is opposing that motion. Now when I add them all up, I get the total work done. Two objects were doing positive work, one object was doing negative work. The total amount of energy transferred to or from it, just add them up. So what is that? 3586? Did I do that right? Yes or no? I did that math in my head. 30, is it 35?
Oh yeah, it's 3586.
Okay. So let me ask you a follow-up question. If work is a transfer of energy, how much energy does that bobsled have after that 12 meters of push?
3586.
The amount of energy transferred to it. There you go. Okay. Number 2, I'm going to have you guys try that one. Okay, so if you're watching this video at home because you missed class today, you should be trying number 2 on your own, and we'll show you the answer here in a few minutes. These people are toiling away. I can see it. And they are computing, I'm sure that they got this. I didn't say anything as they were working on this, but that's what they got. They converted the mass of that object into the weight of that object. They did that by multiplying that 100 kilograms by 9.8. And then they converted the 40 centimeters into 40.4 meters to make sure that we get newton meters out of that. 392 joules of work. Questions at all? Okay, I have a question for you then. In this process, how much work did the Earth do? Take a moment and tell that person that you're sitting next to you. In this process, how much work did the Earth do? Take a moment. Okay, so they're answering this question amongst themselves. I haven't heard it correct. I haven't heard it yet, but someone's going to raise their hand besides Colton and share the answer here. We'll see. I won't tell you who it is. No one's brave enough to go on record. Okay, I turned off the mic. The mic's off. I'm not a liar. No, anyone want to, how much work did the Earth do? Logan, you want to try it?
392.
Except it'd be negative. So the work done by the Earth, notice when I do the Earth's portion here, would you agree that the work done by the Earth, the force that the Earth exerts is downward, while the person is lifting it upward? So they exert the same amount of, the Earth exerts 980 newtons, but for a distance of 0.4 meters, except that the cosine there is 180, so that would be a -1. So in the process of me doing that work, or that athlete doing that work, the Earth ended up doing -392 joules in that process. All right, how much time we got? 1:45. I want you guys to try to answer A, B, and C for that one as a ticket out the door. So for number 3, I want you to take a moment, see if you can do it. A, B, and C, if you're watching this video from home, you should try those yourself. I'll probably end up not having this thing on the video for the recording because we only have 2 minutes left. All right, see if you can get A, B, and C.